Yeah. In this class, we will see how we can compute the collapse loads or the ultimate loads, or we can say the ultimate moment capacity of different types of slabs using yield line theory. So finally, when you are deciding about the failure of a RCC slab, we need to know about the collapse load or the ultimate moment capacity of that particular RCC slab. Now here there are two types of slabs mainly. One is the isotropic slab, another is the orthotropic slab. In the case of isotropic slabs, the reinforcement is same in all the directions. In x direction and in y direction, the reinforcement is same. Or in other words, you can say it has the same value of ultimate moment capacity mu. Across any yield line, the value of mu remains same. That is the meaning of isotropic slabs. Orthotropic slabs means the ultimate moment capacity will not be same along the yield lines. So maybe it may be different in different directions. Normally ortho means perpendicular. So if one direction is like this, another direction you can take like this. So x and y like this. So if the ultimate moment capacity in x direction is mu, so this will be mu dash. So there will be a difference in the value, and that is that there is a relation between those two values. That mu is called as the coefficient of orthotropy. So which is normally less than 1, 0.75, 0.8, 0.9, they may give like that. That means if you take mu as 100 km/meter, so mu dash will be 0.8 into 100 or 0.75 into 100, 75 or 80 km/meter like that. So that is the ultimate moment capacity in perpendicular direction. Ortho means perpendicular. So isotropic means the value of ultimate moment capacity is same along all the yield lines, whereas orthotropic means the values will be different at perpendicular directions or in orthogonal directions. Now this analysis of yield line is done by virtual work method, which you have studied in your undergraduate course. Of course, when you are calculating the collapse load or collapse mechanism, in the case of steel structures also, we are going to use this virtual work method. Anyway, I am not going in detail about that virtual work method. I am going to highlight only the important expressions or the equations which we are going to use to calculate the ultimate moment capacity for different types of RC slabs, which we can obtain, which we can derive from the virtual work method. So I have discussed here 4 important types. So first type is isotropically reinforced simply supported slab with UDL over its entire surface. So consider a simply supported slab. It is having simple support on all the 4 edges, and it is subjected to UDL over the entire surface. That is the thing, and it is isotropic. Isotropic means your ultimate moment capacity along all the yield lines or along all the directions, it remains same. In that case, if you use this virtual work method, so this is the pattern. So I have taken all the 4 sides as simply supported edges, and yield line will be like this. This I had explained in the last video also in the example. In this case, the ultimate moment capacity mu is given by W into L square by 24, which you can get from this virtual work method, which is done by equating the internal work done to the external work done. So okay, so this is the expression for mu. This you have to remember. So here Wu is the collapse load or the ultimate load, you can say collapse or ultimate load. So if you know mu value, you can calculate the collapse load for that particular case. So if you know mu value, W will be 24 into mu by L square. Now second case is isotropic only, but it is fixed. It is fixed. So first case it is simple support, second case it is fixed. So in the case of fixed, it is double hatch. That is the sign convention. And I have told that in the case of fixed slab throughout all the 4 edges, you will be having negative yield line also along the periphery and positive yield line diagonal like this. So in this case, if you use the same theory of virtual work, and if you do, so you will be getting mu as ultimate moment capacity W L square by 48, or W as 48 into mu divided by L square. If you observe this, see here. So So here, if it is a simply supported isotropic reinforced slab, then your W is 24 into this. Whereas if it is fixed, it is 48 into this. That means it is almost double. So it is double that of that. That means a fixed slab can carry more load, or in other words, the collapse load of a fixed slab is double that of the simply supported slab. That is the meaning of that. So it is more stiffer. Fixed slabs are more stiffer than the simply supported slabs. The third case is equilateral triangular isotropic slab with simple supports. So you can see this is an equilateral triangle. All the three sides are equal. So L is the span here. Here also this is L. Please note that this is L. So this is L like this, and this is also you can take this also square. Of course, this is square. Here also this is L. This is L. I have taken square. The rectangle, of course, I will discuss later separately. So this is L. So here also it is equilateral, means all the three sides of the slabs are equal, and the yield line pattern is also identical. You can see here in this case your mu value using the virtual method WU L square by 72. So our WU is 72 times mu divided by L square. So that's what you are going to do. Next, the fourth one is, this is most important, orthotopically. Orthotopically means in the perpendicular direction, your this thing is different. So mu dash will be equal to mu times mu. So in this direction it is mu dash moment capacity. In this direction it is mu. So there is a relation between those two. Mu dash is mu times mu. So mu is the coefficient of orthotropy, and alpha L. So if this is M, this is alpha L. Alpha is nothing but the ratio of shorter span to longer span, maybe 0.8, 0.7, like that. If alpha is 1, it becomes square. Okay, please note that if alpha is 1, this becomes a square, and the yield line pattern will be like this. See the difference between the yield line pattern in square slab and rectangular slab. So this is the yield line pattern in the rectangular slab. So here in square slab it is like this X shape, whereas here it is on horizontal, then fold diagonal like this. So now in this case, if you use the virtual work method, and if you compute the value of ultimate moment capacity for general case, in the general case, so this is the expression. This you have to remember, because in the exam they will give the value of this dimensions of the slab, and mu value they will give. So once they give the dimension of the slab, for example, they give this 3 here, this has 3, this has 6. So 3 divided by 6 is 0.5. Alpha becomes 0.5. Mu value they will give 0.75 or 0.8. Once you know what mu and alpha value, you can always find out the mu value using this expression. You have to remember this. This is very important. You have to remember this. Once you remember this is general expression which can be used for all the values of alpha and mu. Suppose in this case, suppose if it is isotropically reinforced, the meaning of that is mu is 1. If mu is 1, it is isotropically reinforced. That means mu dash mu will be equal to 1 into mu. So that is mu. So mu dash mu is equal to mu means it is isotropically reinforced. So in this case, mu becomes 1. In this formula, if you put mu is equal to 1, so you will be getting, so here this mu becomes 1, this mu becomes 1, root of 1 is 1 itself. So wherever mu is there, if you put 1, you will get this expression. This is the same expression with mu is equal to 1. And lastly, another one special case is if it is isotropically reinforced square slab. Isotropically reinforced square slab means this alpha is equal to 1. If this alpha is equal to 1 and mu also equal to 1. So mu is equal to 1 because it is isotropically reinforced. Alpha is equal to 1 means both these dimensions are same, then it becomes a square slab. In that case, this expression reduces to this form. So if you put mu is equal to 1 and alpha is equal to 1 in this expression, and if you simplify, you will get WL square by 24 only. So these are the some important cases where I have written the expressions for ultimate moment capacity, from which we can compute the collapse load WU or ultimate load WU. So based on this, then I ask you to design a particular type of slab. So in the next class, I will be explaining one design about one of these types of slabs. So this chapter is we can just it is easy. So just read out the assumption, what is inline, assumptions in inline theory, characteristics of inlines and sign conventions, and some examples of yield lines, and these are the expressions derived from the that is virtual work method. So based on these expressions, you can calculate the ultimate moment capacity of the particular section, and for that ultimate moment capacity of the section, you have to design the reinforcement. That's all. So mu is nothing but, here the small mu is nothing but your capital Mu, which we are using in the RCC design. So morning in the last lecture I explained about the design of continuous beam. There capital Mu is nothing but the maximum bending moment. Here this is nothing but the ultimate moment capacity. So we are going to take this value of small value of Mu for finding the reinforcements that is required for that particular slab. So in the next lecture I will be explaining one design on this yield line here.